Hello and welcome back to another episode of the Envisiontech podcast. I'm your host Paul Gagan, and this week I'll be talking about how does programming actually work. In the previous episode of the podcast, I talked about computer parts, which is great if you can understand that. But what does that mean exactly? What exactly does RAM get used for in real life? So in this episode, I'm not just going to talk about those computer parts, but I'm going to talk about how they actually get used and how people who make programs actually run them and what that process actually is. Well, what exactly is programming? Well, programming is essentially writing instructions for a computer to follow. Computers are actually pretty dumb, and you need to give them exact instructions. So you have to tell them step by step exactly what you want them to do, because they can't think for themselves. These instructions are actually written in programming languages. So these programming languages actually define the instructions that the computer should be following. For example, it might tell a computer how it should print something to the screen. There's two main groups of programming languages. And these are high-level languages and low-level languages. So a high-level language is very easy to understand, especially for beginners, and often looks like an actual language. So something that's written in Python, for example, might look like you would expect it to look like if you wrote it in English. They can often run on multiple platforms. So if you write something in Python, it's quite likely that it will be able to run on Windows and Linux or Mac OS. A lot of the work is already done for you with these higher level languages. There'll be a lot of built-in things so that you don't have to essentially reinvent the wheel every time you want to print something to the screen or you want to open a file. They often use a lot more memory as well, though, because part of the problem with having all these built-in things is that they're quite generalized. So instead of telling the computer how much memory you might actually need, it's just going to take up as much as it thinks you might need, which is not usually a problem with lower level languages. Because of this, they also need a compiler or an interpreter, which will then actually turn that code into something readable by the computer. These sorts of languages are usually ones like Java, Python, JavaScript, and there's plenty of other examples of them out there. The second type that I mentioned earlier are low-level languages. These are also known as machine-level languages because they're a lot easier for a computer to understand. They're very difficult for most people to understand because they're not written like a higher level language where it might look like English. Sometimes it just makes no sense at all. There'll just be a lot of random symbols. You'll have no idea what they actually do unless you have a very good understanding of that particular programming language. They also can't be run on multiple platforms because the instructions are usually very specific. So if you write a program, you won't be able to run it on sometimes even different computers. If you write a program for a certain type of device, well then it will probably only work on that type of device because these programs interact directly with the hardware of these devices, unlike with Python, where they have a lot of built-in things in Python that will let it work on Windows or let it work on Linux. Well, when you're writing something in one of these languages, those things aren't built in and you need to actually make them yourself. So you would have to make two different versions of your program if you wanted it to run on two types of devices. They require assemblers for turning the instructions into binary code. So with a compiler, that will actually usually turn the language into one of these lower level languages, and then it will be turned directly into binary, whereas with these lower level languages, you can just turn them directly into binary. The programmer also needs to understand the hardware because, as I mentioned, these programs are built for that specific hardware. So you need to have much more experience and much more knowledge even just to get started with one of these languages, and it can be quite difficult even for an experienced programmer. Um, these also run much faster because they are built for a specific device, and there's not all these other built-in things that are using up memory or are running on the CPU. So it allows these languages to run a lot faster, be a lot more memory efficient as well. Assembly and machine language are two examples of lower level programming languages that you will often see. And you'll see some projects where somebody will write something entirely in assembly, and people will make a big deal about it because it's very hard to do something like that. There's a programming language called C, which has actually more recently been considered a lower level language. But back when C first was kind of introduced, I think 40-ish years ago now, it was actually considered a high level language. But now there are much higher level languages, so C is kind of in between now, just because C will actually let you essentially tell the computer how much memory you want to use for certain things. So it's kind of in the middle of something like Python and assembly, where C is still written in a relatively understandable way, but it gives you a little bit more control compared to something like Python. As I mentioned earlier, compilers are actually the tools that will turn those higher level languages like Python or C then directly into machine code, like assembly or actual machine code. So you can think of a compiler as a translator, essentially. It's taking one language and turning it into another language. From there, those machine languages, as I mentioned, are then turned into binary, which, if you don't know what binary is just ones and zeros. So there are no letters or numbers, it's just ones and zeros. And those ones and zeros represent specific things. So, for example, the number 2 in binary is 1, 0. And the number 1 in binary is just 1. The number 3 in binary is actually 1, 1. Because that first one represents the number 2. And then that second one represents the number 1. So obviously when you add those together, you get 3. So that's essentially how compilers work. And these machine languages will use certain numbers to represent certain instructions. So for example, 01, 00, 1110, for example, might actually tell the CPU to add two numbers together, as opposed to actually representing a number. So that's how we can use binary to actually make CPUs do things. So just to kind of talk more about the process of actually writing a program. So a developer will write some code, right? And in Python, let's just say it's answer equals 1 plus 2. So obviously then answer would equal 3. And that's actually how you would write that in Python. Just answer equal 1 plus 2. And that's all you need to do, right? So as I mentioned, that is how you would expect it to be in English. Now, if you were to write that same thing in the C programming language, it would be int, which just tells the computer that this is going to be a number, answer equals 1 plus 2, semicolon. And the semicolon is just used to indicate the end of a line. So it's a little bit more complicated, but it's not too much more complicated. That still makes sense, you know? But if we wanted to write this same thing in assembly, now I'm not going to read out this whole block of code here, but it is 12 lines long and contains things like the start of this is section.data, answer db0. In here, when we want to actually add a number, for example, it's add space EAX, comma 2 in order to add 2 to the number 1. So if you don't understand that, that's totally fine. It's just kind of to illustrate the difference between these different languages. And I'm going to put this comparison down in the description, just so that if you are interested, you can look at it yourself. Whether you understand it or not is one thing, but just so you can kind of see the difference. So this is a big, big difference. One line of Python or C is 12 lines of assembly. So as you can imagine, as I mentioned earlier, some people write entire games or programs in assembly. This can take years. And writing certain games already takes years, but in assembly it's so much harder. So these higher level languages make things a lot easier usually. But I said they do take away some of your control, because if you were to write that same thing in assembly, it would probably run a bit faster, it might use less memory, etc. So it's a big difference, and a lot of people don't actually use these lower level languages anymore because we don't really need to. The higher level languages have become a lot more efficient than they used to be, and honestly, do you really want to pay somebody to write 12 lines of code instead of one? So especially with how much RAM and how fast computers are nowadays, a lot of companies are willing to take that trade-off now. So how do these programs actually run? Well, as I said, they actually run on the CPU. So the CPU has a set of instructions that it knows how to follow. As I mentioned earlier, a particular string in binary, so particular number in binary, will tell the CPU what to do, and from there it will essentially know how to execute that line of code. Any of the data for that program is kept in RAM. So as I mentioned in the last episode, RAM, or random access memory, is essentially temporary storage, and it's very, very fast. So obviously if you're running something on the CPU, you're going to want very fast access to that. And how it essentially works is when something is kept in RAM, it's given an address, just like how you would have an address for your own home. In RAM, things get an address so that the CPU can know where they are. So when it's looking for, the value for answer, it knows where to find it. The CPU, however, does also sometimes keep some things stored on itself, and that's what we refer to as cache. So the CPU cache is usually very small. So RAM is measured in gigabytes or sometimes even terabytes now, whereas the CPU cache is measured in megabytes. So you might have 100 megabytes of cache on your CPU, which might sound like a lot, but you can't run a game or anything else like that on the CPU. But sometimes there's something really important that you're going to need to access a lot, and you're going to need to access it all the time. So you don't want to slow down your computer by having it go to RAM every single time. And cache is also very fast. And as I mentioned, it's actually built into the CPU, so when you can store something in cache, you usually should. Languages like C and assembly, I believe as well, actually let you tell it what you want to keep in cache. So let's say I'm keeping track of some time or something in C, and I want to be able to access that every millisecond. I want to check how much time has gone by, just to make sure that it's not over a certain amount. Well, I might keep that in the CPU cache, since I know that I'm going to access that every single millisecond, because otherwise the program would have to keep waiting, because it would have to send a request off to the RAM essentially to get that value back. Whereas if we just keep it on the CPU, well then obviously that request doesn't take nearly as long. So that's a really big benefit of using CPU cache over RAM. But in general, programs do run on RAM. And as I mentioned before, the CPU runs programs sequentially. So it'll run it step by step. The CPU doesn't often know what's ahead in the program. So usually it will happen where you might make a mistake in your code and you'll mention something that hasn't actually that you haven't actually told the CPU about yet, and this will cause the program to crash. This isn't as much of a problem in higher level languages, but in lower level languages like assembly, if you try and allocate memory or try and look in memory for something and it's not there, or you're looking in the wrong place, you can actually totally ruin your install of Windows, for example. You might go in there and accidentally delete something. So it's really important to kind of be careful, especially with lower level languages, even languages like C. As I mentioned, you can actually tell it how much memory you want to use. But if I tell it that I want to use all of the memory, well, Windows will be running in RAM. So when you turn on your computer and it, loads Windows and you log in, that's running in RAM. But obviously, if you put something else on top of that, it will delete it from RAM. And that may make it so that you actually can't use your computer anymore until you reinstall Windows. So that's another reason why higher level languages are quite popular, because it's a lot harder to do things like that. The CPU will then send data back to your display or your speakers or whatever output you're using, if it's supposed to. So if you're playing a game and you click the mouse, it will send something to the CPU when you click the mouse. The CPU will do some calculations or follow some instructions, let's say to open a program, and then it will send that information back to your screen. It'll say, okay, this program is now open, this is what it looks like, put this on the screen. When this program actually then stops running, the CPU will then send it to storage so that there's more room in the memory. And as I mentioned in the last episode, storage is actually permanent, whereas RAM isn't. So if your computer turns off, then it wouldn't have that program anymore, which could obviously be quite bad. So that is essentially an overview of how computers run programs and how programming languages actually work. So hopefully this episode and the last one have helped you understand the parts of a computer, what they do, and also how things run on them. So thank you for listening. This is the Envisiontech podcast, and I've been your host, Paul Gagan.